Okay, so now we'll look at the final exercise from the previous lecture, and we will determine which CN axes are present in a molecule of xenon tetrafluoride. Now, because xenon has an extended valence, and because the molecule of xenon tetrafluoride has two unbonded pairs of electrons, the molecule has a square planar geometry, and so first we'll look at the molecule in the plane. So there are two axes for which, if we rotate the molecule 180 degrees, as viewed along this axis, the molecule is identical to its original configuration, so there are two C2 axes. Now, if we consider the axis that is perpendicular to this plane and passes through the central molecule, then we can rotate 90 degrees about this axis, and the molecule is identical. And so this is a C4 axis. And so a molecule of xenon tetrafluoride has one C4 axis and two C2 axes, where the C4 axis is the principal axis of the molecule. Now, recall that in the previous lecture, I made the statement that the dihedral group of order 6 is algebraically the same as the symmetric group on 3 letters. We'll now make that statement more mathematically precise, so we'll start with a new definition. So let the group G, together with the operation star, and G prime, together with the operation star prime, be two groups. A homomorphism from the group G with the operation star to the group G prime with the operation star prime is a function which we'll call phi, mapping the group G into the group G prime, such that for every pair of elements A and B in the group G, we have that phi of A star B is the same as phi of A star prime phi of B. So notice that a homomorphism preserves the operations in the groups that is, for every pair of elements A and B in the group G, we have that phi of A star B is the same as phi of A star prime phi of B, where phi of A and phi of B are elements in the group G prime. In other words, performing the operation star on the elements A and B in the group G is the same as performing the operation star prime on the elements phi of A and phi of B in the group G prime. So new definition. Again, let the group G with the operation star and G prime with the operation star prime be two groups. An isomorphism between the group G with the operation star and G prime with the operation star prime is a bijective homomorphism which again is a function phi mapping the group G into the group G prime. So notice that an isomorphism is a homomorphism that admits an inverse Now, since the function phi from the group G into the group G prime is a bijection, the number of elements in the group G must be the same as the number of elements in the group G prime. And so we can consider the group G prime to be the direct image under the map phi of the group G. That is, the set of all elements phi of A, where A is an element in the group G. Similarly, we can consider the group G to be the inverse image under the map phi of the group G prime. That is, the group of the elements phi inverse of B, where B is an element in the group G prime. And so for every element A in the group G, there exists exactly one element, phi of A, in the group G prime, and for every element B in the group G prime, there exists exactly one element phi inverse of B in the group G. So as a theorem, let G together with operation star and G prime together with operation star prime be two groups. Let the map phi from G into G prime be an isomorphism. And let the element E be the identity in the group G. Then phi of E is the identity in the group G prime. That is, an isomorphism maps the identity element in one group onto the identity element of the second group. So proof: as the element E is the identity in the group G, we have that for every element A in the group G, A star E is the same as E star A, which is the element A. And as the function phi is an isomorphism, phi of A star E is the same as phi of E star A, which is phi of A. So we have phi of A star prime, phi of E is the same as phi of E star prime, phi of A, which is the same as phi of A. That is, for every element phi of A in the group G prime, phi of A star prime, phi of E is the same as phi of E star prime, phi of A, which is the element phi of A. And hence, phi of E is the identity in the group G prime. And we can state the identity since we have already demonstrated that for a group, the identity element is unique. So new definition. Two groups, G with the operation star and G prime with the operation star prime, are isomorphic this is denoted this way if and only if there exists an isomorphism phi mapping the group G into the group G prime. So if a group G is isomorphic to a group G prime, then the groups G under the operation star and G prime under the operation star prime have the same algebraic structure and for finite groups G and G prime, the group G is isomorphic to the group G prime if and only if the groups G and G prime have identical Cayley tables and this is what we call a multiplication table for a finite group. So what do we mean by identical Cayley tables or identical multiplication tables? We'll consider a simple example of two groups of order 4, each of order 4, where the first group has the elements, the identity, and 3 additional elements, A, B, and C. If there exists an isomorphism between two groups of the same order, then the identity element is equivalent to phi of E, which is the identity element in the second group. A is equivalent to phi of A, B is equivalent to phi of B, and C is equivalent to phi of C. And so for any given pair of elements, A and B, we have that phi of A times B, where A times B is the operation in the first group on the elements A and B, is equal to phi of A times phi of B, where the operation on the right is the operation from the group, which contains the elements phi of E, phi of A, phi of B, and phi of C. So let's look at the algebraic structures for the dihedral group of order 6 and the symmetric group on 3 letters. The dihedral group of order 6 has 6 elements: the identity, the element rho, which is a rotation counterclockwise by 120 degrees about the perpendicular axis through the center of the triangle, rho squared, mu, which is the reflection about the line through the center of the triangle and the first vertex, rho times mu, and rho squared times mu. Notice that we can represent this group as the products rho to the power of m times mu to the power of n, where m and n are positive integers, and rho cubed is the same as mu squared, which is the identity. That is, the dihedral group of order 6 is generated by the set S containing the elements rho and mu, where the identity is equal to the product rho to the power of 3 times mu to the power of 2, Rho is equal to rho to the power of 1 times mu squared. Rho squared is equal to the product rho squared times mu squared. Mu is equal to the product rho to the third power times mu to the first power. Rho times mu is equal to rho to the first power times mu to the first power, and rho squared times mu is equal to rho to the second power times mu to the first power. So now let's look at the elements in the symmetric group on 3 letters. The symmetric group on 3 letters has 6 elements: an identity, rho sub 1, rho sub 2, mu sub 1, mu sub 2, and mu sub 3, where rho sub 1 is the cycle 1 to 2 to 3, rho sub 2 is the cycle 1 to 3 to 2, mu sub 1 is the cycle 2 to 3, mu sub 2 is the cycle 1 to 3, and mu sub 3 is the cycle 1 to 2. So notice that rho sub 2 times mu sub 1 is the product of the cycles 1 to 3 to 2 times the cycle 2 to 3. So beginning with the element 1, 1 is mapped to itself in the first cycle and then onto 3 in the second cycle. So beginning with 3, 3 is mapped onto 2, 2 is mapped onto 1, ending the cycle. And so this is the same as mu sub 2. Rho sub 2 squared is the product 1 to 3 to 2 times the cycle 1 to 3 to 2. So beginning with 1, 1 is mapped onto 3, and then 3 is mapped onto 2. 2 is mapped onto 1, and 1 is mapped onto 3. And so this is the same as rho sub 1. So the product, rho sub 2 squared times mu sub 1, is the product of the cycles 1 to 2 to 3, and 2 to 3. So beginning with 1, 1 is mapped onto itself, and then mapped onto 2. 2 is mapped onto 3, and then 3 is mapped onto 1, ending the cycle. And this is the same as mu sub 3. Now rho sub 2 cubed is the product of the cycles 1 to 3 to 2, 1 to 3 to 2, 1 to 3 to 2. So beginning with 1, 1 is mapped onto 3, 3 is mapped onto 2, 2 is mapped onto 1, cycling out 1. Beginning with 2, 2 is mapped onto 1, 1 is mapped onto 3, 3 is mapped onto 2, cycling out 2. 3 is mapped onto 2, 2 is mapped onto 1, 1 is mapped onto 3, cycling out 3, so this is the identity. And mu sub 1 squared, the cycle 2 to 3 times the cycle 2 to 3. 1 is mapped onto itself in the first cycle and onto itself in the second cycle, cycling out 1. Beginning with 2, 2 is mapped onto 3, 3 is mapped onto 2, cycling out 2. Beginning with 3, 3 is mapped onto 2, 2 is mapped onto 3, cycling out 3, and so this is the same as the identity. And so the symmetric group on 3 letters contains 6 elements, which we can list as the identity, rho sub 2 squared, mu sub 1, rho sub 2 times mu sub 1, and rho sub 2 squared times mu sub 1. That is, the products, mu sub 2 to the power of m times mu sub 1 to the power of n, where m and n are positive integers, and rho sub 2 cubed is the same as mu sub 1 squared, which is the identity.